expected that no, it's not that low. It could be 0.5 or 1%, and you multiply that by the formula that I showed you. The chances of finding intelligent life is about 10 raised to 6. So anywhere in between, depending upon you expect a life elsewhere or you don't expect a life there, the answer may be somewhere in between. What we have found so far. Next. The next one. This point I want to emphasize is that when we look for life elsewhere, we should not look for identical human being or a being which is just very similar to plants and animals that we have known. But we are conditioned to look for only those things that we know. But we have to consider that life may not be like us. It could have been even silicon-based life. It could be very built on a different elements. And silicon, as I said, is a likely candidate. The reasons I have discussed earlier. And what we want to consider is that we should be open. When we look for life, we should be open about what kind of life that could be, not just our replicas. They may be our cousins by some sense, but they are not necessarily like us or like our plants and animals or microbes. The next one. If you look at Earth, there are certain places where life conditions are very different than what we see on the surface. And for example, there are some places which are very hot, some places which are very humid, some places very cold, some places where there is a high pressure. For example, if you see 10 kilometer under sea level, the pressure of the water is so high, but still there is a life. There are living organisms we have found there. So such, what we call it, extremophiles, also teaches us that please look for life which may not be like your life, but their life can adjust and can develop in a very extreme conditions. What happens in extreme condition is that for most of us, when there is too much of heat, our proteins get denatured, and when they are denatured, they are non-functional, and the system doesn't work. So slight variations in temperature actually makes the protein denatured and non-functional, and that is what happens in most of the organisms. But the extremophiles have learned how to survive this. The next one. Next one. They have learned how to survive extreme temperatures, pressure, salinity. You know, the sea water, which is almost 2 molar saline, and there are organisms which can very easily live in that water. And pH, extreme pH, acidic, basic, dry conditions, and heavy radiations. So there are places even on Earth where the organisms have adapted to this kind of extreme conditions. We call them extremophiles, and example is that very the high pressure vent under the sea level, where the temperatures are very high, the pressure is very high, salinity is very high, but still the organisms can survive. And these are the conditions. The next one, that we have acidophiles, alkalophiles, anaerobic, endolith, which you can survive in the rocks, and likewise. So we should be open to these ideas that organisms can adapt to any extreme conditions, and therefore the life elsewhere could also be very different than what we have seen here. The next one. So you can see that deep sea hydrothermal vents, and this deep sea is about 10 kilometers. So 10 kilometers, you can see the water pressure. 10 કિલોમીટર પાણી ઉપર હોય તો એનું પ્રેશર નીચે કેટલું હોય, એ પ્રેશરમાં પણ organisms can survive. The next one. Now, where we have been so far. This is our Earth, and we have been to Moon. And our next target is that we want to go on Mars. Uh, uh, there are plans to take man to the Mars. The distance to Moon is only about 400,000 kilometers. This is as far we have gone now, 400,000 kilometers. The distance to Mars is about 50 to 60 million kilometers. So at least 200 times further than Moon. So we have some experience of traveling to Moon. Now we have to learn how to travel to Mars, which is about 200 times further. It takes about 3 to 4 days to go to Moon, and it will take about 6 months for a one-way trip to Mars. So our task is that we have to develop these capabilities where we can put people in conditions who can survive the zero gravity in the space and give them a comfort level in a way that they don't harm themselves and they still reach to Mars, do their experiments and come back, and that will take about 2 years. So we are preparing to put people to the Mars in a round trip way, but it will take a long time for their journey into the space. Now, these are the other planets which are even far away. So our ability to physically go there and examine for life is very limited. I don't think we would be able to go much beyond Mars because the other planets are even hundreds of times more further away than Mars. So our challenge of physically going there is limited. Our ability to go there is limited. So we will have to look for other ways of examining if there is a life. And one way to do is to send missions without man, robotic missions. They will collect a soil sample or rock samples, bring it back, and then we see whether there was a life. They will bring the images from other planets, and we can examine the image and then try to figure out whether life could have been there. So this is the challenge that we have. And so these are the ways that we look for life on other planets. One other way is that sometimes we have objects falling from the space on Earth, and we can examine those rocks and those materials, meteorites, what we call it, and look for fossils on those kind of material. The next. This I was referring to meteorites, and we look for evidence of life on those material, whether that existed there. And sometimes we can do the cosmochemistry in the lab. That if suppose we know that on Mars this is the composition of the soil, this is the composition of the gas in that air, and then we can do simulated experiments on Earth, just like what I showed you earlier. That under those conditions, whether compounds which are represented in living forms can be generated using the conditions on the other planets. The next one. So let us see realistically where should we expect living forms of life. You see, from Sun, we are the third, Earth here. On the other side, there are Mars, and we were talking about Mars, and we are planning a mission there. So Mars, there is a good evidence, and I will come to tell you that there is a good evidence that life could be there. There is a lot of water and many other conditions conducive for formation of life. Similarly, then there are particular moon for Jupiter and Saturn. Just like our moon, these planets also have moons. And these two moons are also very much Earth-like and a potential candidate to look for life on the moons of these planets, not on these planets, but on the moons of this planet. The next one. So, in our solar family, we expect a good chance of formation of life. Doesn't mean life is existing now, but life could have been formed or can form in the future in Mars or Europa, which is a moon of Jupiter, and Titan, which is a moon of Saturn. So these are the three places where we can expect to see the formation of life. This is the Mars surface, and as you can see that it looks very much like some of the places on Earth, the rocky as well as this kind of rock formations. The next. And we have sent many missions on Mars, unmanned missions to Mars, and starting from 76 onwards, we have been on Mars, we have sent missions on Mars, robotic missions, and more and more indications of plenty of water is found on the Mars. And surface, I showed you the topographical surface, and the small and large scales water and water channels are expected to be present on Mars. The next one. So there are a lot of geothermal and hydrothermal systems. There are lakes and valley networks at different temperatures. So that's a one condition which looks very much similar to Earth. There are ancient oceans as well as water in outflow channels and gullies. So there are flowing waters, lakes and channels, and there are some ancient oceans. That means there were oceans, but now it is not under oceans. A Martian wet environment with larger residence times of liquid water. Residence time means water is there for a long period of time, enough time for life to develop. So Mars is one likely planet right next to us, and we are preparing to send a manned mission to Mars. So far we have sent only the unmanned missions to Mars. The next. Now, the habitable environments, as I have told you, that beside Mars, can also expect to see in Europa and Titan. The next one. This is a very recent paper about Titan, and this was published, I think, a couple of months back, just last month, and in Nature Astronomy. And this indicates that there are active methane-based hydrologic cycles on Titan. We are now talking about a moon, of Saturn's moon. And it has a complex geological landscape, making its surface geologically diverse. In fact, this paper has described the entire geography of Titan. So it tells where there is a lake, where there are rocky formations, etc. And it's like a mapping of a Titan. And different materials, temperatures, and gravity fields, many of their surface features are similar, products of the same geological processes. The dunes and lakes are relatively young, and hummock-like mountains or terrains are the oldest on Titan, and dunes on the equator and plains of at mid altitude, and labyrinth of terrains and lakes on the poles. So the geography on the pole and on the equators are quite different, and has a lot of hydraulic systems that are indicative of presence of life. The next. So in our planet system, we have discussed that three likely candidates, two moons of our neighbor planets and a Mars. These are the three candidates. But these are only suggestive that there could be life either in past or may develop in the future, but there is no evidence of actual living forms as of now, but likely can be there. Now, if we think beyond in other galaxies, uh, we have found that outside our solar system, there are about 4,000 planets. There are moons, and the moons, we have identified about 4,000 planets in the stars which are not our sun, but in other part of the galaxies. And out of that 4,000 planets, exoplanets as we call it, is outside our solar system. Most of them are not likely to be habitable because of their orbits are outside the habitable zone. And a good number of them, planets with part of the orbit in the habitable zone, and there are planets with entire orbit in the habitable zone, about 129. And out of 190 planets which have most of the orbit in the habitable zone, 24 of these are possibly rocky. So I told you about solar system. Now I'm telling you about outside our solar system in our galaxy. Out of about 4,000 planets that have been identified, there are 24 of them which have a habitable orbits, as well as their topography suggests a rocky, possibly rocky surfaces, and that is something for future for us to explore whether we should we should be looking for life in this subset of the exoplanets that we have identified. Next. The Nobel Prize for Physics this year, 2019, went to these three people. One of them had developed